Hello, everyone. This is another weekend, another Saturday, and we are here at Microsoft Zero to Hero community. I'm Shahab, the host for tonight's sessions, and I hope you're having a good time wherever you are on this blue planet. Let me bring up share my screen. So, at Microsoft Zero to Hero, this is a community created by the community for the community. It is shaped by your ideas, your learnings, your efforts, and everything that we could share together. And you could go to microsofthero.com, and there you could follow us on various social platforms, and also like see the news and all the upcoming things uh, on our portal. Also, we are part of Microsoft Learn, and if you go to the calendar, there you could see what are the upcoming sessions. We have two upcoming sessions already confirmed about observability and how to use alerts, and also like AI-enabled applications in .NET and Azure. But today we will talk about testing the tests, and Stefan is here with us. Without further ado, I would like to invite him on the stage, and he will answer more questions in this regard. Hi, how are you, Stefan? Welcome.
Hello, Sharp. Hello, world. I'm doing great. I've been quite looking forward to another Microsoft Zero to Hero, being on the other side of the
Yes.
camera.
Thanks for participating. You're one of the constant guests on every session. You're present on every session we have every week. So that's amazing.
Oh, it's
Cool.
great content.
Then I don't want to keep everyone waiting. Please tell us how we could test our tests. I will share your screen now. Go ahead.
Thank you so much. Before we test our tests, just a little bit about myself. Hello, I'm Stefan Pölz. I am from Vienna in Austria. I'm a Microsoft MVP, just freshly renewed, a JetBrains community contributor, a co-host of the .NET Devs AT meetup in Vienna. So if you're in Vienna, then please definitely let us know. Also a co-host of the To Code or Not to Code live stream on YouTube. If you want to check that out, we can exchange links later. As a matter of fact, on my GitHub profile, I have all of the links to all of my socials. If there are any questions that I cannot answer within this hour, or if you are watching the recording of this session. We'll be talking about mutation testing, what it is, what it can do, and in particular, then we will dive into the .NET tool called Striker. Well, Striker is available for JavaScript, for Scala, also for C#, also a bit of F# support, but we'll figure this out all within the next hour. Now, let me start with a little story. It's a real story, but all of the code is altered, all of the names are altered, but it still shows a use case of where mutation testing helped discover a bit of a problem with a test. So at some point in my projects, I had a type similar to this, a so-called operation. Yeah, well, essentially represents something that can be started, that can be stopped. And when we stop it, it can either have no error, meaning it is successful, or it can have an error. So we can track the duration of something and whether it succeeded or not. And we also, of course, had tests. Now we just, for this demo, super simplified tests. We're not covering everything, but just to show that running the tests should pass so that we get a clean stage. All right. Now, this operation, at some point, we introduced support for iDisposable. Because it was kind of tedious to always use it like this, like a little bit of a demo. So we could start an operation, then do work. And if an exception happened, usually then having a try catch, where we do the work. Let me just disable this for now so we don't get too many pop-ups. So whenever this work fails, then we stop this operation with that exception. And otherwise, if it succeeds, we stop it regularly without passing an exception. But this pattern, stop. Now, this pattern was quite pervasive. And at some point, we figured out, hey, wouldn't it be nice if we could use the using statement? So having a using, where we now in that using start the operation, do our work, and essentially should an exception happen in there, it will always finish automatically, but still that we are able to, with a try finally, when we do our work, we actually can, catch, of course, stop our operation, but we no longer had to have the regular in the finally do the stop or the stop at the end. So it simplified the code a little bit, and some liked this using declaration more. So we essentially made this type idisposable, generated the idispose method, and essentially called stop in there for syntactic sugar. But we essentially had a little bit of a bug that we didn't notice because we didn't test it thoroughly. Actually, in here, this operation would be stopped twice, once here, and with the generated finally block, also calls stop. So if there is an exception, we call stop with that exception, and regardless, we call stop. But if we already stopped with an exception, with some error, then the second stop should be no op. It shouldn't do anything. Mm-hmm. If there was no exception occurring, if it succeeded, then this stop should record the time when it was stopped. So we had a little bit of a bug. So we added a little test, which kind of looked like this.
But the stop in the finally is because of the idisposable, right?
Yes, exactly. So we could also kind of convert it into the full-blown code, where we have another try finally around, or we could also have it as such. So we have our operation, do our work. If there is an exception, we stop with regular, and finally we call the dispose or just the regular stop. So this kind of pattern. And then, we had, then we got, the actual fix was to say if we actually have a stop time, meaning, is it stopped? We had that property. Is it already stopped? Then do nothing. Oops. Just return out of there because we don't want to record another time there. It says already been stopped. It can only be stopped once. So kind of a bit of a safeguard. Now, keep in mind, this is not thread safe. We could also do this in a thread safe manner, but let's keep this demo simple. And we said, this is the fix. It's easy enough. And we had a test case generated. And essentially, this is what got generated. And we see it here immediately. Operation doesn't exist, but it was actually part of the pull request or merge request that we had. And we had CI in place, and CI, when we run a .NET test, discovered that, this doesn't even compile. And not compiling means a failing test. With a failing test, the solution was safeguarded. So we go back as a draft and said, hey, we actually don't have this interface operation. Let's change this to the actual type that is available. But what we then had is actually this. Here we kind of indicated, if actually an error is occurring, but let's make it simple. So we stop the operation here. Now, when we run this test, it does still fail because we're actually not recording an error here. Now, let's record the error, call the correct stop. And the test succeeded. Now, when what we also had in place was test coverage. Now, we didn't at this point take test coverage super seriously, but we did look at it from time to time, in particular on the impacted test. So to see, a new test has been added. Let's go to operation. A new test has been added, and let's see if the new test is actually covering all the scenarios. And actually, I actually already gave the solution away. But what we had, our scenario, what we had is that we actually called the code that was changed, but we actually had a problem in our test. Our test at some point in the stage was looking like this. Sorry, I was jumping one stage ahead. We were just checking if it has stopped, and we also checked the time. So we were using this fake time provider. We were also doing the check with the time, but to keep it simple, what we had in place was essentially only this. And the test looked good. And when we run the test, it passed. And when we run the code coverage result, sorry, I'm winding back a little here. I gave the solution already away. We also saw, that this operation, this stop method, and this is stopped with including the return statement, was actually covered. But we had a problem in our test because this test, although running this new code, because stop is called once with an exception and once implicitly from the finally without an exception. So what we have essentially then have a dispose, which is effectively then calling the parameterless stop as well, implicitly. So the code was covered, but it actually was not asserted. The test was not asserting the actual change, that we actually have the error. The test is passing if we just look at the changes, like in GitHub or GitLab or Azure DevOps. If we just look at the changes, we usually take a peek at the changed code. We see, okay, we have this safeguard here in place. Looks good. Taking a peek at the test. Okay, a test case has been added, some assertion. Let's assume it was test-drivenly developed. In this case, it wasn't, so should be good. Okay, LGTM. But we actually weren't asserting it. So if I was to remove part of this code, the test would have still passed. And this is where mutation testing can come in. So if we now run our mutation testing suite, in this case, this is striker.net, it discovered that there is actually still a problem with that test. What mutation testing is doing, it's taking a look at the production code, and you can configure it to not observe the entire code base, but only stuff that has changed since the last commit to main or some branch. And then it would go ahead and maybe instead of an error, or instead of null, setting something that is not null. Mutating this line, this is where the name is coming in, mutation testing, and then running not all of the tests, but all tests that really cover this line. If this test isn't even covered, then we don't even have it covered. So we can make changes to the production code without the test failing. If this line is covered and the test still passes, we still have a problem because the test is actually not asserting. The test is covering this line, but it's not asserting any of the result. And this is what mutation testing can unveil. Okay. It unveils not uncovered code, but unasserted code. And in the meantime, Striker should have completed. And if
Stefan, we have a question, which I think maybe is the most relevant part, because you were talking about like what is a mutation testing. The question is what is the difference between mutation testing and unit testing? Is mutation testing regression testing?
It's not quite, no. So there is no mutation testing without unit testing.
Mm-hmm.
You need unit tests to apply mutation testing. If there is no unit test, you can't do mutation testing. Because mutation testing is now, we see it's actually mutating our code. We can take a look at which changes have what this tool actually changed. It is changing our production code. For example, changing a Boolean expression and just negate it.
Okay.
And now at least one test must fail.
Yeah.
Otherwise, this code might be covered, but it's not asserted. So we do need those unit tests.
Okay, so in the mutation
builds on unit
testing, so in the mutation, does the library or mutates the line of codes of the production, or is it changing the line of code in the test, or both?
No test is changed. Only production code is changed.
Okay.
And then tests are run, not all of the tests, but impacted tests, so tests that cover that production change. And then at least one test must fail.
Okay.
If no test is failing, then we have code that is not asserted. So our tests are not 100% efficient.
Okay, so it's also not about like only coverage or not about like what you had in, but also like whether these asserts are actually doing what they supposed to do, and
Exactly.
nothing is escaping from their eyes, kind of.
Exactly. What we can take a peek at is for stuff that doesn't even have coverage. Okay, so none of these actually have coverage. So if code that isn't covered, you don't need to run a test in the first place. There's no way to mutate it because, well, it's not even covered. If it is covered, but nothing is happening, for example, this return statement is removed, now at least one test must fail. But no test failed. So this mutant that was generated in production code survived.
And okay, so there is a branch now in our production code that seems to be covered, but not really asserted very well.
Exactly. Okay. If we go to the code coverage, it's covered. But if we go to mutation testing, it's not asserted.
Got it.
No test is failing if we change
that. I hope the question from Stefan was covered by Stefan.
Very good. And all of the mutants and code that actually is mutated, like this, is stopped, a Boolean expression that is negated. And now a test actually fails, means it is asserted and the mutant has been killed. So we want to kill, hence the name of the game, Striker Mutator, kill the mutants. It's a bit of a play on, I think that's X-Men 2 from 2023, I think, not entirely certain, where there's Colonel Stryker using the X-Men and mutants, weaponizing them. But yeah, the character says mutants can be useful at times if you control them. And yeah, it kind of fits to that scheme. And with mutation testing, as part of our CI, we can uncover if the tests could be a little bit more efficient. And if we were to do what I actually gave away earlier and add those missing assertions too, now those mutants would not survive because we actually assert all of the properties, and everything would be green. And we now not only see that the production code is covered and tested, but also the test is quite efficient in asserting and safeguarding the behavior.
So I assume it doesn't matter, like if you're writing like XUnit or like the way we are testing. Probably it's not matter. Like if I do also snapshot testing, right? If this test still survives or not survives, then it's also an indicator that something is wrong there.
Exactly. A test must fail. Striker supports, I think all of it now also has, well, it used to support MS and or VS testing. It now also has experimental support for the new testing framework, Microsoft.testing.
Platform.
Platform, indeed. Thank you. It's empty. It's MTP. I always have to then. Yeah. It has experimental support for it. That means it now not only supports XUnit, NUnit, MS Test. It also supports TUnit. So it's not bound to a testing framework in .NET. It's kind of bound to a testing platform, and then any kind of test would work as well. It doesn't matter if you use, like here, XUnit for the test, or if I was, and for assertions, maybe I wouldn't be using XUnit. Maybe I was using Fluent assertions. I don't have it installed, but it would look then this should be true, because all of the testing frameworks work the same. If a test or if an assertion is failing, an exception is thrown, which will mark the test as failed. And if a test is failing, then a mutant is killed.
So it's not about the testing framework. It's more about the runner or the platform that they are running.
Exactly, which is the cool thing in the .NET ecosystem. You don't really need to change your tests. Well, actually, you shouldn't change your tests. You plug in Striker and see. Well, the first time you add it to a new project, the result can be quite well. You realize that your tests might not be, that there is a lot of red, a lot of surviving users, but that's how it is. I also don't say that you need, just with code coverage, you don't need to aim for 100%.
Yes.
What I came to love about mutation testing, if you make it part of a review, I mean, now with automated tools, you can also run it in an automated fashion and then analyze the result in an automated fashion, and have with a good design skill, then give it some severity. Hey, well, this mutant is surviving, but it's maybe an argument not null check missing, or I'm just making something up. So maybe nothing too impacting, but hey, there is an if check. If this true turns into fault, which is happening a lot, maybe we should add an assertion there. So it gives another metric to the quality of our tests, and with that to quality of our project. But as with every metric, don't view it in an isolated fashion. View it with the rest of your metrics: code coverage, code review, AI reviews. They all come into play.
Cool.
So let's go into more. Maybe let's take a small step back again, and really take the time to see how mutation testing works under the hood. We now had a little bit of more of a complex scenario, so let's take a peek as an easier scenario. We have mentioned what mutation testing is. It does make small, and the key portion is isolated modifications to our production code. Isolated means it makes one change once all of the tests, or all of the tests that cover that line, so all of the impacted tests, and then one test must fail of this suite of impacted tests. And then the next change does not include the first mutant. So all of these mutants are isolated and run in an isolated fashion. Each of these modified versions is called a mutant. And if at least one test is failing, we kill the mutant. This is good. If a mutant survives, this is bad. Well, not necessarily super bad, but if there is a lot of surviving, it can indicate a problem with our test suite. And this then, it doesn't say anything about the production code. The tests say something about the quality of the production code, and if the mutation testing now says about the quality of our tests. In combination with code coverage, that gives the quality of coverage. Mutation testing gives the quality of assertions in our tests. Also already mentioned the difference. So we have it supplements code coverage in a nice fashion. Now, super isolated example. Let's assume a calculator, and we have a method add. We can add two integers, two int32s, and we just say plus. Then we have a test where we call this method, and we assert that 1 + 2 indeed is 3. We run the test passes. Mutation testing now comes along and mutates this line. Maybe it changes this plus into a minus. Now a mutant has been generated. All of the impacting tests, I suppose we have many more tests in our test suite, but those other tests, well, they might be calling other methods. So this other method does not impact this change, or is not impacted by this change, so this test isn't run. We want to do the tests that actually cover this line of code. So the impacted tests, we run the tests. One test is failing, mutant has been generated and killed. Then we go back to the original code and generate a new mutant. Maybe we do a division or a multiplication. We could also consider swapping these two around. But for an addition, since additions are commutative, I hope I'm using the correct mathematical term here. It doesn't matter whether the left or the right portion of the addition gets swapped, the result will be the same. Then we take a look at another source code. Again, we have a minus here. We change the minus to a plus. We created a mutant. One test must fail. It fails. Mutant has been killed. With, for example, division, you actually could change the left to a right because division is not commutative. Now the test should fail, and it does indeed. Mutant has been generated and a mutant has been killed. One mutant could also be, hey, actually don't do anything, just return the default, which in this case, the return type is an int. So let's return 0 here. Does the test fail? Yes. If I would have a test that always returns 0, then we would have, or yeah, if we would have a test that expected actually 0 as a result, that would now mean that we might want to add another test to it that doesn't result in 0, so that we tighten the effectiveness of our test suite. So this have been some arithmetic mutants. There is also Boolean mutants, such as changing an AND to an OR. Now we have more than one tests or assertions. At least one of them must fail. One does fail, so mutant generated, mutant killed. And this game not only works for operators, we could also have for comparison operators. We could change the less than or equal to just a less than, or the less than or equal to a greater than. But it also works for like link methods, changing an all to an any. Yeah,
cool.
And it must be, since it has a compatible signature, and now at least a test must fail. Yeah. Well, I guess we can't change it to a select. Well, actually, we could change it to a select, but now this doesn't compile. Yeah. Which is also a mutant has been generated and has immediately been killed because it doesn't even compile. Yeah. This comes into play. Maybe we have an analyzer, a diagnostic analyzer that usually gives, exactly those squiggly lines. And maybe there is a warning. Maybe we have a warning, don't use any. Yeah, I'm just making something up here. Yeah. We are not allowed to use any in our code base because we forbid it, and this creates a warning. Or actually, if we say warnings as errors, this is now creating compiler error, which now would mean this code doesn't compile, and again, a mutant has been generated and been killed. Not compiling means fail.
One question again from Stefan is just to clarify: does mutation testing discover false positives, tests that are wrong but tests are passing?
Tests that are wrong but tests that are passing. It should. It should. Well, when it comes to assertions. Let's say, well, actually, let's come to our plus example. Let's say we say 2 + 2 = 4. Now, right plus left, that should work. So this test is passing, all good. What if we used the multiplication instead? Instead of plus, we say multiplication. It is not quite next to my key. Actually, on the German keyboard, it's on the same key, but just with a different modifier. So on my German keyboard layout, this could actually be an honest mistake. Yeah, but the test is still passing. Yeah, because 2 plus 2 is the same as 2 multiplied by 2.
Yeah.
So what this now indicates is that we might want to add another test. I'm making it so, just assuming we are now adding another test here, that is now instead not only adding 2 plus 2, but maybe also 2 plus 0 should be 2. And in this case, now this test will fail. So I'm not sure if this quite answers the question, but yeah, it not only discovered a bug, but it also made our test suite more efficient. So we have then multiple. Usually, you then I can't do it in here, but usually you then have a theory.
Yes, with multiple
X unit or
parameters,
some
yeah.
data. Yes, and then you say 2 plus 2 should be 4. 0 plus 0 should be 0. 2 plus negative 2 should be 0, and so on. So you have more data than just one input. And now our test is quite efficient in covering all of the potential problems that we could make with this very simplified addition.
Yes. And Stefan is also saying thank you in advance. Okay, Stefan, if it is not covered, then please feel free to write in the chat and I will bring it up. Thank you.
Sweet. If we jump into the Striker documentation, Sharp already, I think, put it into the chat. We see Striker supports. It's now, how old is this project now? Several years, more, 6, 7 years. Not entirely certain. It's been out there for a while. There's arithmetical mutations, there is equality mutations, there is logical mutations, Boolean, like also a Boolean expression, just adding negated in the beginning. We have now initializers, like changing an array that has 2 elements to an array with 0 elements, or vice versa, changing an array with 0 elements to an array that has some elements. We also have removal mutators that just, remove a return or remove a break or a good old go-to. And then again, one mutant code is removed. If this removal makes, because if this wasn't a regular return, but maybe a return 1, maybe now if we remove that, maybe now not all of our code paths actually return a value. Well, this would result into a failed compilation and the test still failing, mutant generated, mutant killed. Unary operators and so on. We also have to link mutators, and we only got half of the list. There is many, many more. There's also regex mutators that change a regular expression, and test regexes, of which I'm usually scared of. So there is actually Striker.net, or all of the other Strikers as well, Striker for Scala, Striker for JavaScript. They're quite mature. They offer a lot of mutators. They also offer a lot of configuration, but we'll come to that in just a bit. What kind of mutation testing techniques are there? Again, taking now another step back and taking a look at how would you implement mutation testing? How do you mutate original code? Well, we of course could mutate the source code. The big advantage, this is what Striker does, the big advantage is if we change code, then you can easily just display the change to the user in a report, like the report that we saw earlier. You can super easily show it. Hey, we applied here the negation mutator. This was generated, looks like this, and it was killed by exactly this test. So it's super easy to display diagnostics to the user. But it is actually then quite bound to the language. So a C# source code mutator only works for a C#. But what about Visual Basic and F#? Well, we would need separate mutators for the Visual Basic language and for the F# language as well. To make it more language agnostic, we could mutate bytecode. In the land of .NET, well, we could actually mutate IL code, which all of the .NET languages actually compile to. But then it gets a little bit harder to get back to the original source code? Well, you can for sure emit debug symbols, which makes it easier again. But in particular, in release mode, a lot of optimizations get applied, and the diagnostics will not have as high fidelity as with source code mutations. So there's pros and cons to everything, of course. The big advantage with bytecode, well, it's bound to be faster because that's code we can immediately run. Or in the case of .NET, IL code, we then compile into machine code. I'm here on a Windows x64 machine, and then run the test. If we were mutating source code, we first need to compile the C# code to IL code, and then this again to the machine code in order to run it, which just takes more time. So kind of per definition, per technique, source code mutation is a bit slower than bytecode mutation, but has higher fidelity. So we have pros and cons there. Now there's a technique called mutation switching, or as it is implemented in Striker, called mutant schemata, which is trying to combine the advantages of both to kind of only compile once, but still get super high fidelity. Striker does this by injecting all of the mutants immediately. So there is not 7 different compilations for the 7 different mutants, but there's one big mutated source code. Well, I mentioned that each mutant should run in isolation, so not that one mutant is impacting another mutant. This should not happen. And Striker is implementing this as such. So actually, let's take a look at a little bit of a FizzBuzz example. I kind of built this after a job interview where I implemented a FizzBuzz. So it's with the rules. If it's divisible by 3 by 5, we do the FizzBuzz and FizzBuzz. If it's both, implementing these rules. Now, mutation testing could come along and say, hey, this string, this non-empty string, we change into an empty string. And if it was an empty string, Striker would change it to a non-empty string. And this AND operation to an OR operation, negating this, what we saw earlier, applying all these mutants, but kind of all at once, but guarding them with more ifs, which then kind of looks like this. So it inserts an if. If this mutant is active, then run into this code. This is actually the empty mutant, not doing anything. Otherwise, we kind of run into the next code. Well, there is another mutator that does nothing, or we call into this debug assert that I had here. And then here is like
this boss builder that the Striker created, like a source generated file, or
not by a source. It is generated, but not by a source generator.
Okay.
So this is generated only once during the invocation of the tool. There is no like compile built-in solution, because that would need running all the tests. So this would slow down the compilation quite a bit. So it's part of the tool chain. And well, it's actually then totally new source code. So the old project is kind of replaced, because with source generators, you can only add additional code. Well, you could use interceptors to some degree, but interceptors only work for ordinary methods. An ordinary method is, this would be an ordinary method, but it wouldn't work for constructors, for properties, destructors, finalizers. They are not ordinary methods. It wouldn't work for these. Or a local function like I have here, it's also not an ordinary method. So interceptors would only work. So a source generator-based, a Roslyn source generator-based technique wouldn't work too much.
Yeah.
And when it comes to actually to the fizz and buzz, where we do the division by 3, we see that a couple of mutations are generated, and they're all guarded between this is active, and they all get their IDs. Or again, having a mutator that removes this code overall. So if you take a look at the diff, we see that Striker is adding a lot of code. In white, we see my original source code. And in green, we see lines that have been added. And in red, lines that have been changed. And we see that Striker is actually changing and adding quite a lot of code. But all of this, we can take a look. At the end, we see there is 69 mutants have been generated for this. Well, actually, we start here at 46 because I did it for the entire project, not just this document. So we have, what's that, like 30 mutants in this file. Now we compile this only once, and then map which of the mutants are covered by what tests. And when we come to that mutant, we say, okay, now mutant 46 is active, and we run all of the tests that are impacted or that are covering this change, and then at least one test must fail. And we repeat this for all of the mutants, and this way we only need to compile once and run many times. So we kind of get off but still get super high fidelity when it comes to report. So we get the best of both the binary and the source code, the bytecode and the source code world. I listed here a couple of tools. I checked. This has been an older list where there has been more experiments, but there has been an experiment. I think it was Textura. I'm mixing it up now. One of this was actually a Visual Studio plugin, trying to plug it into an IDE. But usually mutation testing is run in a CI system or by some automated system. All of these projects, they are no longer maintained. So when you are writing for .NET, or what we also saw, C# or C# or F#, JavaScript or Scala, then go with Striker. Those are from what I saw, the best maintained tools for these ecosystems. Now with Striker, it's just a .NET tool. This means it's a console application that is packed in a NuGet package. We can take a look at this. NuGet package is called .NET-Striker. So we can get to nuget.org, go to .NET Striker, and see this is actually let me zoom in. This is a tool. So we can install this on the command line. Let's take a look at which tools have I installed. We can say .NET tool list -- local. You can install .NET tools in a local and global fashion. In a local fashion, I installed these tools here, and here is .NET Striker, and then we can just invoke it. .NET Striker -- help, and we see all of the commands that Striker supports and all of the options. You then pass usually a solution. You pass in the project and also the test project, and Striker pretty much figures out the rest. But there is more that you can configure. But to complete the tool section, you can install a tool. You could also install it globally. Then it's available as part of the machine, like in anywhere in the command line or in any directory. If you install it locally, it's only available in that directory and below. But the big advantage is it then kind of becomes part of your source code repository. So if we take a look at, that's essentially the repository that I have here. I can link this later if you want to take a look at the source code. We have here a .NET tools.json where we have all of the tools that we have kind of locally installed and their version. With newer versions of .NET tools, we can also enable roll forward, which means .NET Striker, I think this is now running on .NET 10. If .NET 11 comes out, but the tool hasn't been published in .NET 11, we can kind of roll forward to our local latest .NET version that we have installed. But if there are breaking changes between .NET, well, there is breaking changes, usually super corner case, but yeah, stuff could not work. Just be aware. Usually works, but there is always this one case where it doesn't. So you can install it globally or locally to be part of the repository and also version it so that everybody is working on the same repository also has the same version of the tools. And we can also pass a configuration. I mentioned configuration already. I want to take a closer look at configuration. This is just a JSON file. Most of these configuration you can pass either via the command line or via this JSON file. I do kind of like the JSON file because, again, you can make it part of your repository and then have it checked in and also have changes to your Striker configuration part of a review. For example, I ignored a couple of mutators here. You can ignore entire sections, so all of the logical mutators are ignored, so they're just not generated. And you can also say, hey, I don't want to have the link first and link some mutator applied, where, well, link first would be changed to a link last and vice versa. So if some mutations or category of mutations don't apply to your source code or kind of has false positives, you can ignore them. You could also start with a new project. You see maybe, oh, there's way too much. Maybe let's focus on some part. So you could ignore some mutants and then ignore less and less over time to not have this full load, but it might take a bit of time, but then improve every time just a little bit. You can also ignore methods to mutate. For example, well, let's ignore all of the log methods because usually I barely test logging. So all of the log error, log warning, I don't want to have mutated because I don't test usually logging. It's diagnostic information. Because otherwise a mutant for the logging methods would be generated. No test is asserting or even covering it, and then mutation test fails. What I also usually don't test is configure await. When you await a task, you can say configure await and then pass either false or true. Well, there is now also configure await options, which is an enum, but yeah. This is more of an infrastructure code, and sometimes to improve performance. When you write library code, where you don't know if it's once on a ASP.NET Core application or on a UI application, then usually say configure await false. But Striker, of course, would change this false to a true and then expect the test to fail. But well, I rarely have the test configure await because that's actually an analyzer. I have an analyzer in place that forces me to use the correct configure await. And then producing it as an error. So yeah, well, a test would fail because if I use configure await true, it would fail my analyzer, but it's just wasted work because I know already that it will fail. So I also ignore this. And there's more to ignore. And again, you can start a bit more. You can ignore broader and then ignore less, well, depending very much on your solution. And one section is also that I like a lot. You can also use configuration to not run the entire mutation tests every time, maybe with every pull request or merge request, because that's actually a lot. Depending on your project, this can run from just a couple of seconds to 30 minutes to maybe even hours, depending on the size of the project. So the more mutants are generated, the more tests you have, the more impacted tests run, and so on. And maybe if your tests aren't super fast, then mutation testing also takes longer. It's heavily depending on the mutants.
Sorry.
No, go ahead.
Do you maybe suggest maybe we have I don't know, a cron job every night or something to run the mutation tests?
That's actually a good point. I started out with having a nightly run of the full suite, but I wasn't checking it on a daily basis. Okay. Even weekly is quite a lot. What I do these days is actually running it on demand. From time to time, I run the full report and take a look if I see some patterns that show, oh, this one file has 80% failed mutants. Maybe the tests that we have for this set of functionality aren't too great. Let's create an issue, a ticket for future investigation, something like that. Okay. I started out daily, then I did weekly. Now I just do on demand. You don't do this all the time, to be fair.
Yeah.
What I do like though is to run it on every pull request, but only on the actual changes. So you can target main. Well, I have it disabled here for demo purpose, but if you enable it, you can then it essentially looks at the changes, like git diff style, sees, okay, this was changed, this code was changed, and this code was changed. So only for these changes, mutants are generated. And then all of the tests run, all of the impacted tests are run. So if you make it part of a review every time, with every change, you'd get a little bit more to review. Maybe just take a look at the report, see, does it look all right, good or bad, maybe needs a bit of improvement, or open an issue or ticket for later improvement. Just a little bit more of review, but it, over time, you then also start seeing tests a little bit differently. I have the feeling, since I did mutation testing, I write tests more forward because I already see, oh, this will be mutated. Do I cover this? So after a couple of years, you kind of are your own. You become your own. You already do it at design time in your mind. Your testing will become more efficient, kind of out of the box. And if you tie it into an agentic code environment. And I'm actually not sure. I haven't checked too many. I'm not sure if actually Striker is this. This would be maybe the next holiday project. If they haven't, perhaps they have already. If there is a skill that helps figuring out the LLM to improve the tests.
Yeah, that was all like my question. Like, have you tried, like, because in an agentic environment, you have the changes, you have the report from your striker.net, and then you could like ask an agent like to fix the tests or create some new tests like to cover those cases as part of the same pull request, and then see if it works.
Actually not, but now that we talk about it, this is going to be my next project. What you can configure is like a threshold. You could say, well, this is already like super aggressive. Usually I don't have it that aggressive, but like you get a green check mark, everything is good when you have, in this case, 100% of the mutants have been killed, 100% test effectiveness. You get a bit of a warning if it is in the low section, and if it is 80%, if only 80% of the mutants were killed, then you can actually break CI. So .NET Striker will then return with a non-zero exit code. So I only used this as a bit of a quality gate. But to actually feed that results back into a tool, I haven't experimented with that. But now that we talk about it, yeah, I think you're just nerd sniping me. if this hasn't been created, maybe this already exists and you just pull in the skill and be good to go.
Yeah.
I need to. Perhaps this will be a blog post to follow up with. And yeah, you can also configure like timeouts, don't run longer than X, but I usually don't have good experience because a full one does take a while. So yeah, I usually run only the changes on every pull and merge request. Then you can also mutate, configure reporters. There's different reporters that Striker is offering. We already saw the HTML reporter. You can have a different CLI reporters. There's also the dashboard. The dashboard is a project where it is free for open source projects. You can sign in, link it up with a project, and then get it automatically get those reports automatically shown in the Striker environment or ecosystem that the developers provide. You can have various reporters. What we saw earlier, what is really cool is what I come to kind of find quite intriguing is running the tests or running the mutation testing now. So they're starting the .NET Striker tool with my configuration. Now this covers all of the mutants and all of the impacted tests and starts mutating them. It says, 49 mutants found. Now it opens the project already. All is 0 because behind the scenes, the tool is still running, and it now starts. We see those S's is Striker mutant has survived, and it still runs. It still runs, and this report is actually updating on the fly. So when it takes a while, you can kind of see it build up and run through your test suite if you wanna see it working. If you want to give Striker a try, you can go to the website, and already mentioned the dashboard. There's also the playground. And this is an interactive application where you can change code and run code without having anything installed on your system. This runs entirely in the browser, WASM style. You don't need .NET installed. You can just play with it. So we see here a couple of mutants. We see the tests are not super efficient. There is one time missing, so we can run the tests. We can also run Striker, which is now all in the browser, now running the .NET code, WASM, Blazor WASM style. So you can, if you're not sure yet what it is, you can get your hands here dirty without installing anything, and play around with what happens if I change a little bit of code and see how mutation is done. While this is running, there is one more section I would like to go to.
Before you go to that section, I shared a link to the Striker repository that they have a skill for the agents to how to run the Striker. So I think it's more on the usage part.
With the configuration,
Yes.
So I guess a skill to feed back to it and then improve, saying, hey, if it is low, make it high. Then the tool needs to change, or the LLM agent needs to change the tests, then run Striker again and see if it has improved indeed or went worse. Yeah, actually, I need to play with skills a little bit more.
Good.
But that's really cool. Thank you very much.
Sure.
Still, while this is running, since it's running on my system, I'm sharing and having all stuff. This will take a bit. I want to see. Go into the integration portion. So what does exist is Striker has a plugin for, there it is, for Azure pipelines. This is an older plugin. We see this is, it's running on an older Node version. This is kind of out of life. This is not really maintained anymore, but I still kind of find it cool. So it plugs into your Azure DevOps pipelines. You can plug it in with your unit test results. You can plug it in with your code coverage result. This comes out of the box with Azure pipelines. And you can also plug it into your mutation test report and then get still the very similar HTML experience in there. And you can take a look at the calculator and see that in this very calculator, I have a divide, but I actually do a multiplication, meaning that my test suite isn't as efficient as it could be. So going to the calculator tests, to the division test, well, I divide 1 by 1, which is the same as 2 plus 2, which is the same as 1 divided by 1 is the same as 1 multiplied by 1, so this mutant survives. So what I alluded to earlier changes into a theory, doing inline data, then saying, okay, 1 and 1 should be 1, and also divide 10 divided by 2 should be, do not embarrass myself, 5. We have int left, oh, sorry, what is this? Yes, int left, int right, and int expected. Passing them down. Now, this will cover this mutant, and I now made my test suite already more efficient, and I can add another test case super easily. Now, is there magic involved? No, it's not. You could actually write your own mutation testing tool. Don't do it. Striker is super mature, it's super cool, and it's continuously maintained. They do releases every other month, I think. It has a whole set of mutations, but you technically could, because it's just .NET code. Striker is based on Roslyn, so that's the .NET compiler platform. You can use the compiler to, well, write your own compiler or code analysis code. In particular, there are those Microsoft.codeanalysis.star packages. Everything that starts with Microsoft.codeanalysis is essentially the Roslyn compiler, minus the typos. And for example, the Roslyn compiler is available for C# and Visual Basic, not for F#. That's a different tool chain. And you can use like the workspace packages where you can build or you can analyze solutions and projects. And what you could do is write like a syntax walker. That's just how it calls, which just goes through each and every node of your source code. Just to show briefly, if you have never seen this, we can take a look. Let's take the calculator. It's super simple. We can take a look at how Roslyn sees this code. So every document, that's a file usually, it's like a compilation unit. We see we have a file scope namespace declaration, and we see here our C# syntax tree with all its fidelity. If we would add a comment, it would show up in here as well. We have our class declaration. In our class declaration, we have method declarations. These method declarations have a parameter list with 2 parameters, the 2 doubles, and we can inspect all of these. So you can walk this syntax tree. And this essentially was what is Striker doing under the hood, just in a way more sophisticated manner than I do here for this demo. Essentially check, hey, is this node, I only support arithmetic mutations here in this super simple test. Is it an add or a subtract or a multiply expression? And if it is, we will add arithmetic mutators. And if it's the add, we extract those nodes and understand, like we have the left expression, what is on the left-hand side of the plus, what is on the right-hand side of the plus, so that later when we emit new source code, because you can change the syntax tree as well. Well, syntax trees are immutable, but you can create a new syntax tree where instead of the plus operator that we have here, we now insert a different operator, and then emit this new source code and have the tests run against that. And then at least one test needs to fail. And we can also run, where do I have that? I have this mutate-custom script, which is essentially now running my custom mutator, now running mutations against the calculator. And we see that here this num1 plus num2 operation has been mutated to a minus, to a multiplication, to a division, also to a remainder operation. 3 of them have to be killed, 1 have survived. Yeah, this is essentially what Striker does under the hood as well. Now, in the meantime, the playground should have completed. No, it has not. This is now depending, on machine, I'm streaming and such. But do give the playground a try. Play around with Striker, and if you like it, then check out the documentation. It's described how to download the tool and use the tool. Start small and see if it actually can make your tests a little bit more efficient. So this is really the main use case is not to find bugs in your source code. Sometimes you do, but that's not the main use case. The main use case is to make your tests more efficient. So to come to a little bit of a conclusion is it complements test-driven development excellently, just like code coverage reports does. And I have the feeling, for me, it works best for library code. So for general purpose code, it doesn't need like an application to run, doesn't need a UI to run. It works best there from my experience. As with every metric, to go a little bit to the danger zone, don't see, just as you shouldn't see code coverage as an isolated metric and say we need to aim for 99% code coverage, don't see mutation scores as the silver bullet that should be 100% or 99%. But do use it in your flows from time to time, because well, as it did for me, I have fair certain if you're using it here and there, you will start writing your tests a little bit differently. You see, there is something that I haven't asserted. Perhaps I should. It not only helps making your tests more efficient, it also helps for your coding. Maybe we can also train then LLMs based on that to get better results. So that, yeah, we always shift a little bit more to the left. When it comes to application code, as I mentioned, when there is an UI involved, or when you actually have to deploy your application, maybe to a Docker container, then the experience is not so great. Because usually then you also lose the connection between, if you're not testing code that you just invoke, if you have like integration tests or system tests where you invoke APIs, you don't really link the mutant, the changed source code to the actual test. It theoretically works, but it's not the best experience. Not really the first use case for mutation testing. Also, if you want to test infrastructure, didn't have a great experience there, because usually there are just no tests for infrastructure. So mutation testing requires unit tests. If there is not a single unit test or not a single test, then you can't run mutation testing. What you need to be aware of if you're not using Striker, the result heavily depends on the available mutators of the tool that you're using. As we saw, Striker has a lot. And it also depends on your production code. If there is nothing to mutate, then, well, no mutants will be generated. One thing to keep in mind that this might be low running, very depending on how many mutants are generated and how many tests you are, that are impacted, and how fast your tests are, and the system that these tests, they usually run on a CI system that is not the fastest. This might take a while. I actually have one demo here, if I have the tab still open. For this, it's still kind of a smaller project, but it's testing analyzers. So there's a lot of Roslyn. It kind of uses Roslyn to test Roslyn. This just takes a bit. There's a lot of logic involved. And for this case, it actually took, why did it say 1 minute? Oh, wait a second, that's the wrong project. I wanted to check. This project, we had actually run for, I think, 20 minutes. This is what I wanted to show. No, pipelines. So we saw, this actually runs for 20 minutes, but that's the full report. As mentioned, these days I run it on demand when I want to get a bit of an understanding the current state of the quality of my test suite. But do run it on a change, only on that change as part of your CI with the correct configuration in whatever you use for the CI. And for the last mention is, since I mentioned CI a lot and also mentioned the Azure DevOps plugin, now for GitHub, there isn't such a cool plugin as for Azure DevOps. But just what you can do easily is generate yourself, oh, there's the mutation report, generate yourself an HTML result or a command line result if that suffices for you. But the HTML result is super cool because I can then take a look at the impacted code and link it back. Oh, where did I click? And actually see what mutants survived there, and you can filter by the survived mutants and see, there's something that I don't test here in this Roslyn code. Create this HTML report, and then if you're on GitHub, you can easily use the GitHub upload artifact that is then part of your CI, uploads this file. And you can emit a warning if it hits a certain threshold, indicating that you might want to take a look at it. Where you could say, if tests are added and the mutation score is like 0 efficiency because all of the mutants have survived, then there might be something wrong with that test, and you could find this problem with the test case that was added already during the review, super early, and not later when it actually something blows up in production.
Perfect.
And now I'm wondering if there are some.
I don't see any questions at the moment. There were a couple of questions during the session that we covered, hopefully. And yeah, if there is any, please feel free to add it in the comment sections. Thanks, Stefan. This was as always very fruitful and revealed like a new way of thinking about tests, at least for me. Um,
Oh yeah, I definitely have. What I really realize now talking about it, I do write my assertions now a little bit differently now after.
mm,
I think we're using mutation is now for 4 years, so I do write my test, or I pay attention. These days, I don't write too many tests manual anymore, but reviewing tests, you kind of see the patterns, yeah,
yes.
and you see potential mistakes already quite early. If there is no questions coming in, then do reach out to me on any of my socials that are linked on my GitHub
Yes.
profile, or if you're watching the recording, then if there is anything that I can help with mutation testing, please do let me know.
The links I already shared in the channel. And yes, so also follow Microsoft. Go to the microsofthero.com. Follow us on other social networks, LinkedIn, Twitter, and YouTube. And then stay tuned for the upcoming sessions. Thanks everyone for participating. Thanks, Stefan, for this session. And
Thanks for having me.
everyone, have a nice evening.
Goodbye.